In this lesson, we will go through the steps of setting up and running a static structural analysis on the same simple lattice example from the previous follow-along, but using the beam elements method instead. You can download the starter file below to follow along with this video. And again, we want to simulate this lattice with compressive load applied to the top plate and also fix the bottom plate. So we'll start the same way by creating a new section called Analysis and adding the static analysis block from the search bar. We need to fill out the FE model and the boundary conditions. So we'll double click to get the FE model block. And in this case, we need to have two components, so we'll add one item to the list. One of these items will represent the lattice structure with beam elements, and the other component will be the plates that have solid elements. So double clicking into the first item on the list, we can select the FE lattice component block. For the second item, we will choose FE solid component. We'll need a mesh for each with the corresponding element type. So in this lattice mesh input, we'll double click and choose the FE lattice mesh option. We'll make this a variable and rename this lattice mesh. For the FE solid component mesh, we'll double click into it and choose the FE volume mesh, which is the standard block and approach that we do for any other solid element meshing. I'll rename this to plates mesh. So let's start with the solid element meshing of the plates first. We will fill it in with all of the steps that we use for the standard, but since this geometry is quite simple, we can skip the remesh surface block and go ahead and put in mesh from implicit body block right away. And for the body, we'll use the plates. I'll choose the initial tolerance of 0.5 and take a look at what that looks like. We have some rounding here, so I will need to sharpen it. So we can either do this by selecting that sharpen box, or in this case, will use the second overload of this block and add a sharpen iteration of 1. And that looks better. And now I'll add an edge length in the volume mesh block of 1 to start. And let's take a look at the cross section by pressing X. And make sure it's the right block that we're viewing. The elements are a bit large, so we'll decrease this value to 0.25 millimeters. It's important to have a finer mesh for that interface with the lattice so that the connection nodes can be more easily established. And now for the volume mesh, I will choose linear. And so we can move on to fill the lattice mesh block. Using that lattice body, we can drag that into discretization and choose the geometric order of linear. And if we isolate this, we can see the beams that have been meshed here. I will leave the subdivision at 1. Now we need the lattice beam thickness parameter, which is already a variable, so we can drag that in. For material, we can drag in the materials we already have for both components. And I'm holding Control here to copy that chip over to reuse in the second component. Next, we can go in and fill out our boundary conditions, which will be our load case. We need 2 items on this boundary conditions list. One will be the force and the other the displacement restraint. And I will make this a variable to help with the organization of the notebook. Double clicking in to choose the force block and the displacement restraint block. And for the boundaries, we can turn on that plate's mesh visibility and select that face using right-click menu and choosing the flood fill option. And then we can drag in the selected boundary and add in our force vector of 0, 0, and 1,000 newtons in the negative Z direction. We'll do the same thing for the displacement restraint face as well. And now if we try to run the static analysis with all of these inputs filled out, we will get an error because we have two separate FE components but haven't connected them. So to do this, we'll need to grab the tie constraint block, which will be a block that we use to establish independent and dependent nodes between the two components. And for each of these independent and dependent inputs, we need to have boundary selected. And so we can do that by double-clicking into that input, selecting FE boundary by body block, which will allow us to select the nodes on the mesh within that entire body of the component. So we'll do this for both the plates as well as the lattice. And if we turn on the visibility of the tie constraint block, we can see the nodes that are selected. And depending on your geometry, you will need to adjust your tolerance. For this example, this tolerance is good enough. If you increase that tolerance, you'll be able to grab onto more nodes that are further away from that interface. But now that we have that tie constraint established, we can make that a variable, drag that into our connectors input, and let that static analysis run. I'm going to make this a variable and call it analysis result. You can also go into the properties of the static analysis block to see and find those results, and use the heads-up display to visualize the results of your analysis.